I've been asked to announce that that overflow supply of lecture number 1 is here on the platform for those of you who didn't get it this morning. They promptly ordered 100 for the crowd to take care of this afternoon session. I had notion to tell them that it would shrink to 75 by the afternoon session because the first session is always larger. But I don't know. I believe there are 100 copies around here somewhere of the afternoon lecture, so you can get them. Before starting on the afternoon lecture, I wanted to say a couple of words about a few things that transpired this morning. You remember I mentioned iodine reacting on the surface as a catalyst down in the temperature region in which the high surface area that we talked about this morning on coal would be retained. This is in line with the enthusiasm that I have for making sure that we don't overlook anything with respect to this original surface of coal, whether it can be utilized in any profitable way in any of the processes that we may be interested in developing. Attention was called to the possibility that the iodine is more than a catalyst in that system. I'm afraid, I think all of you are aware of the very nice work that's been done on intercalation of halogens in graphite. A graphite chunk will just swell up like nobody's business if it's exposed to bromine, for example. Now, iodine may have the same intercalation properties. Another good example is potassium atoms in graphite. The Tamaru in Japan has shown will spread the layers of graphite apart to the point at which the adsorptive properties are completely changed. I think this is something that hasn't been demonstrated in the case of iodine. It's quite possible that when you put iodine onto coal, that you do intercalate the iodine and spread some of the coal layers so that you might even create a very much larger surface than exists there to begin with. But the particular paper that I referred to discussed the iodine and the HI only as a catalyst, and we're not aware of any intercalation, if indeed it does exist, for the iodine system under the conditions they were working. Incidentally, they disclosed, as I glanced back through this paper, which is by von Krevelen, and I'll mention it more in the lectures Friday, as a matter of fact, on liquefaction. They mentioned that the first work on iodine on coal was done by Berthelot in 1869. So this business of working on coal is a rather old business. As I stated this morning, I introduced the subject by discussing physical and chemical adsorption because I wanted to get around to the question of surface area and pore distribution in coals. But now we have to face the real properties of coals and see what happens when coals are heated up to temperatures higher than this 350 degrees or so that is the limiting temperature that one can heat coal to without disturbing the original surface area. And quite properly, I think the simplest procedure is to take up next what happens when we pyrolyze or gasify coals by simply heating them up to a high temperature. The question of surface area in regard to this high temperature work is a separate one. I don't think I'll go into it very much, but temperatures have been measured for chars that are formed by heating coal and pyrolyzing it to 400, 500, 600, 800, and so forth on up. And in general, the answer is that you don't get very much surface area developed until you start oxidizing the char. When you start oxidizing the char, you develop enormous surface areas. But the surface area that is left after one has heated the material to the point at which the coal becomes gooey and starts to pyrolyze and mess around, the char that is formed in that does not have a high surface area, more the order of 4 or 5 square meters per gram, and not up in the hundreds of square meters per gram that the original coal had. At any rate, it behooves us to look into the various ways of treating coal. There are going to be 3 main processes considered. One, the gasification or pyrolysis of coal. Tomorrow's lectures will go into the, well, more strictly speaking, the graphitization. Now that's what I mean. The pyrolysis, really, of coal. I'm trying to think of another word which is on my notes, but anyhow, I better get my notes up here too. Carbonization of coal. Carbonization or pyrolysis of coal. Tomorrow, the gasification of coal in the sense of converting it with steam and air over to carbon monoxide and hydrogen. And finally, in the last day, the hydrogenation of coal to liquefy it, desulfurize it, and at the same time consider all of the desulfurization processes that we have to talk about. So this talk then is going on with a continuation of the subject of coal, but paying more particular attention to the carbonization and what happens as we heat coal up. Historically, this is a very old subject because beehive ovens have been used to produce coke for blast furnaces for many, many years. Of course, in this case, the volatile material and the things we're looking after now were all simply sent out to perfume the atmosphere. The later coke ovens have helped to retain some of the tar and some of the gaseous materials, but even those, as I point out in the notes here, being heated up to 950 to 1100 degrees centigrade, retain and permit one to recover only very small amounts of usable materials. Something like 6 or 7% tar, for example, in addition to 10,000 cubic feet of gas. This, I think, is from a ton of coal. The 6 or 7% tar is from any amount of coal, but the 10,000 cubic feet of gas, I think, is from, 1 ton of coal. So these old processes are well known, but the tricks that people have been working on recently have had to do with carbonizing coal in such a way as to be able to get a high liquid recovery and a useful gas recovery. And anytime one carbonizes coal or pyrolyzes coal, one necessarily leaves a lot of coke around, or char as we want to call it. Now, the char is going to contain sulfur, and so something has to be done with the char if one is going to utilize that portion of the energy that's in coal, and one has to do something about the sulfur. But the things we're talking about this afternoon are more concerned with getting tar and thus liquid products out of pyrolysis processes, and then we don't consider in too much detail what happens to the char. It can be used in different ways, and we'll suggest some of them. Several processes have been developed. I'm not an expert on these processes, and I feel very much at a loss when I talk to some people who have been visiting some of these pilot plants and huge installations that I have only a book description of. I've never seen any of these pilot plants or any of them in operation, so I don't have nearly the feel for it, but there's little consolation in the fact that there are people in the audience who will be able to answer any questions that come up, because I'm sure there are people here who know these plants very much better than I do. The first one in line that has received quite a little bit of publicity is the Garrett Coed Process. I sometimes wonder whether it got a lot of the attention because of the fact that it's owned by Occidental Petroleum. Occidental Petroleum seems to have a habit of being in the forefront of international affairs and various interesting procedures of one kind or another, including the possibility of their stock all being bought with the Standard Oil of Indiana and the company no longer existing. But at any rate, the Garrett Coed process is a rather unique one, and one that is worth considering for a moment. I think I have a few transparencies that I want to show along about this time. First, a general one pointed out by Weiser. Incidentally, any of you who don't have a copy of this book might be interested in it. There's some very nice discussions in here. This was the W.F. Libby Laboratories Coal Conference held in Santa Monica in September '73. There's a very extensive discussion by Weiser from the University of Utah, who's in charge of their coal work, or at least in charge of part of their coal work there. I'm not sure there's none in the libraries, but I'm sure you could get a copy of it by writing to the W.F. Libby's laboratory in Santa Monica. Weiser points out that as a basic principle of coal pyrolysis, coal carbonization, one has to consider the formation of radicals. This is simply a chunk taken out of that diagram of the coal molecule this morning and illustrates the cleavage at a CH2 group with the formation of two radicals. Now, coal carbonization will produce many such radicals. The fate of those radicals will determine how much liquid, how much gas, how much other product you're going to get, how much char you're going to get. If these simply recombine with other bigger fragments, they quite clearly can form char. On the other hand, if there's a means of transferring hydrogen atoms or methyl groups or some entities to these that close these radicals off, one can get some of the lower boiling material formed, gases or liquids. Now, next slide there, next transparency. As a ready example of furnishing these hydrogens, Weiser pointed out the trick that tetrazone pulls of being able to transfer 4 of its hydrogens very readily to such molecules and form naphthalene. This is simply a typical hydrogen transfer molecule, and this is believed to take place without catalyst. There's always some question as to whether the ash in the catalyst is performing a part function, but I think hydrogen transfer can take place non-catalytically, so that these hydrogen atoms could go into radicals of the type that I mentioned a moment ago. On the other hand, if one wants to keep this as a hydrogen transfer agent, one has to put hydrogens back on the naphthalene to form tetrazone, and that presumably does take a catalyst. The catalyst in some processes may be nothing more than the ash. Incidentally, in the notes this morning, in the very last line of the notes under composition of coal, I mentioned the inorganic materials. If you look carefully through it, you'll be surprised to find that the symbol Fe is not included. I think in the last line I put GE, and I think somehow or other my writing, the Fe got converted to GE, so you'll make that correction. I'm aware of the fact, in other words, that there is iron in the ash of all coal. So this is typical of what takes place in pyrolysis, and also the possibility of sealing off these radicals, removing them from further activity, or diminishing their activity anyhow by passing on hydrogen atoms to convert the radical into a molecule. Next slide. Coming now to this schematic flow sheet for the Garrett Coed process, the unique feature of this process is the way in which the coal is heated to begin with for pyrolysis. Pyrolysis is an endothermic process. One somehow has to furnish heat for it. Now, in the combustion processes we'll be considering tomorrow, this is done simply by adding steam, which is endothermic with this reaction, and oxygen, which is exothermic, and the two of them come out with a self-sustaining thermal situation. Here, the heat is brought into the coal by admixing in this first chamber hot char. The char is the product from pyrolysis of the coal, is made hot by heating with oxygen in a very low time of contact system here, in which the care is taken that the product is primarily carbon dioxide, it being possible thereby to get the largest amount of heat per unit amount of carbon loss that can be obtained. If you permitted carbon monoxide to form, it would be much less efficient thermally. So by producing hot char and then circulating and admixing that char with the coal, the original coal pyrolysis is carried up to the point at which it can take place. And from there on, one gets the gaseous stream off and purifies it. One gets liquid phase out. And one finally gets a residue of char. The total production is something like, I don't know if I have it mentioned here or not, but it's the order of 56% char, and I think about 27% liquid plus a certain amount of gas that comes out. But this is one of the more discussed anyhow. I'm not sure how it stacks up when I say more favored. It's publicized. Again, I'm very hesitant to compare these various processes because economically I don't know whether this has a chance to be important or not. One very, what I would call naive statement is made, and that is that the char that is formed is very porous and very reactive and can, quote, be easily desulfurized, unquote. Now, I'm a little hesitant as to the easy desulfurization of any solid material, but this is in the articles that have been published on the Garrett process, and some of you who know it better than I do perhaps know how they're going to succeed in desulfurizing the char so it can be burned in a power plant. Otherwise, it has to be burned in such a way as to permit the removal of SO2 by flue gas scrubbing or something of this sort. So this end is the first of these pyrolysis processes. It is a huge advance so far as liquid products are concerned. usable products are concerned compared to the old ovens that were used in preparing coke and just catching what gases they could at high temperature. But it still leaves a char containing a lot of sulfur as one of the compounds, one of the products. The second system I want to consider is this char oil energy development called the Coed Process under the auspices of the FMC Corporation. The next slide. Now, the whole flow sheet for the entire plant is much too complicated to put on, but I did want to put on just this portion concerned with the Coed Pyrolysis to show you the unique feature of the system. The unique feature of the system is that one reaction vessel here at around 675 degrees or something of this sort, Fahrenheit, is used as the first stage in the pyrolysis. Then there are 4 other stages, one here, well, no, there are 3 other stages, which are operated respectively at around 800, 1,000, and 1,600 degrees Fahrenheit. To the 4th stage comes in a gas feed containing a lot of air, which then forces a stream of gas countercurrent through the 3rd stage and the 2nd stage, but not back to the 1st stage. In other words, this furnishes the heating that is necessary to heat the systems up. It pyrolyzes in total all the way from 600 degrees to 1,600 degrees, but the products coming off the 600 degrees are not subjected to oxidation, and therefore come out and join the other streams with retaining much of the products that came off in the original pyrolysis. So this is a controlled pyrolysis system in which the pyrolysis is held at low temperature in the 1st stream, and then the 2nd, 3rd, and 4th stages are progressively heated up higher in a stream of air to furnish the necessary heat for this higher temperature pyrolysis. Now, from this, the claim is made that they get a yield of 20% liquids, 17% gases, and 55 to 60% char. Here again, the same problem with respect to char exists as in the Garrett process. One has to get the sulfur out of the char. There's too much in to permit it to be burned. The particular write-up that is made a year ago on this Coed process proposed that they might use the Kellogg molten salt process, the sodium carbonate fluid reactor system, in which they burn the coal in a molten bath of sodium carbonate at high temperature by injecting steam and air, so they could adopt this as the 2nd stage of their process and thereby convert the carbon over to carbon monoxide and hydrogen and take the sulfur out in the usual fashion. Again, I would hesitate to make a comparison between this and the Garrett process because I don't know how the 2 of them stack up economically. The economic calculations represent a subject all by themselves, and all I know is that this is one of the processes that is prominently considered among those that are carrying out pyrolysis and carbonization as part of their processes, and winding up thereby with about half of their carbon still there in the form of a char. Next, I wanted to turn to an item that is little related to what we said this morning because it brings in my favorite subject of surface area, but I think is one that might very well be considered at this point because some of these processes we're going to consider make use of it. And this is a question of preventing the caking of coal by exposure to oxygen. It is well known that in the processes we're going to consider tomorrow for combustion, it is necessary in some of them to get a pre-caking process in to prevent the coal from messing up on the grills in which combustion takes place. And even in some of these carbonization processes, the pre-coking, or rather the pre-treating with oxygen has been used. The Dutch workers, for example, used it in connection with their work on iodine hydrogenation of coal. 2 workers at the Gas Institute Lee and somebody else whose name is in the series of references here, studied the behavior of, we have it already with us, the behavior of coal as a function of the amount of oxygen treating. They found that to prevent caking, it was necessary to get a certain amount of oxygen fed into the system. Starting here with a small amount of oxygen going in, they finally get up to a point here at which they've received enough oxygen to prevent caking. In other words, this is free flow material up here. And this work seems to indicate that if the amount of oxygen picked up is something in the order of 1 cubic foot per pound of coal, it will prevent caking. Now, no specification is made as to how much of that oxygen is picked up by the coal and how much of it is used to carry out a little combustion, because there's a 10% weight loss in the coal, which can be water, volatile materials, and so forth. If we assume that this oxygen is taken up by the coal, then just as this morning we pointed out that 200 cubic feet of methane per ton of coal would amount to something like 10% of a monolayer, so this figure of 1 pound, 1 cubic foot per pound, or 2,000 cubic feet per ton, constitutes a monolayer of oxygen in the average coal. So taking again, since I don't know the surface area of this particular coal I use, but taking the average for bituminous coal as being somewhere around 200, 250 square meters per gram, the amount of oxygen that you have to put in to prevent caking for any of these processes for which you may want non-caking coal is somewhere in the order of a monolayer. This is the second point that has interested me in connection with the surface areas of coal. Now, how a monolayer of oxygen is going to prevent caking, it seems reasonable that if you coat these little cubes or platelets of coal with oxygen, they might be less inclined to stick together than otherwise. Whether this simple picture has any significance or not, I don't know. But the fact remains that the average consumption of oxygen that's necessary, and there are several trials on preventing of caking of coals, is somewhere around a pound per cubic foot, which, as I say, is about the order of a monolayer of oxygen. This is the item mentioned at the top of page 3 of the notes. As the next item, I've included solvent refining. Solvent refining is ordinarily considered as a separate process in treating coal, but in this particular case of solvent refining, they combine it with heating to a temperature at which pyrolysis of coal will take place. So I consider it a sort of a pyrolysis treatment for coal in the presence of a liquid acceptor of one kind or another. And in particular, the process that I have, and my slide operator is very efficient, he anticipates what I need here, is the Src process. Developed, I think, by the Spencer Chemical Company originally. I guess that's where the Src comes from. And this is now the Pittsburgh and Midway Coal Mining Company. In the process, the finely divided coal is admixed with a solvent and heated up to around 800, 825 degrees. Now, at such a temperature, one gets the ordinary pyrolysis of coal that you would expect, but it's in the presence of a liquid. The liquid that can do a lot of things. It can even furnish hydrogens or small groups to saturate some of these radicals that are formed, and thereby prevent the formation of more char or solid products. It can increase the amount of liquid formed, in other words. Somewhere I thought I had a figure on the amount of liquid formed. Oh, yeah. Oh, no, I don't have it. Anyhow, they get a good yield of liquid product. These processes, a process of this sort, among other things, will remove the pyritic sulfur The sulfur that is present in organic form as a pyrite will come out, be separated out here in a high temperature filtration process. And so the inorganic material, the ash, the iron pyrites and the like is removed, and therefore the inorganic sulfur is taken out. The organic sulfur still remains. And this will be a high sulfur content fuel that can be taken care of in different ways. I think they burn some of this for the heat and then remove the sulfur by regular sulfur removal processes. Now, as a final item, let's see, do we have any more slides? Weiser, again, in this booklet, compares the results of straight pyrolysis so far as the fraction of the material converted into liquid form is concerned with a pyrolysis process compared to this so-called dissolution process. The actual dissolution process that he's speaking of has in the liquid phase some hydrogen transfer agents such as tetralin. So they could be helping to convert the material over to a liquid form. As one can see here, the pyrolysis yields a much lower final liquid product. The dissolution, both carried out at the same temperature, is much more efficient in catching the pyrolysis products and converting them over to liquid form. So there are certain advantages to using a solvent recovery system, and some here I know have visited this particular Src solvent refining unit and know a good deal more of the advantages of it than I do. Finally, I just wanted to say, in regard to the hydrogen donor systems, that it is well recognized and has been recognized with the Bureau of Mines and other groups working in coal for many years that certain molecules such as tetralin, I use tetralin as an example, holding hydrogen, can readily transfer these hydrogen atoms to coal constituents, adding them to radicals that are formed to form liquid products, and thus greatly decreasing the tendency for polymers to form, forming char, and increasing the amount of liquid form. Whenever these are used as a major component in a reaction, they usually provide a catalyst also, because the hydrogen re-pickup by the resulting products such as naphthalene I showed you in an earlier slide has to be done over a catalytic system. And in some systems in which it is carried out without a catalyst, presumably the ash is the catalyst component. This, in brief, then, is a summation of the principal processes that have been proposed for pyrolysis. And I think this is a good place to stop and throw the meeting open to questions, because I hope that there are people here who will be able to answer a lot of the detail that I won't be able to answer in regard to some of these items. Thank you. Are there any questions? And I guess we still don't have a microphone, so I'll have to pass this one on to anyone.
Can you give us an estimate of the approximate lifetime of one of the free radicals before it would either recombine with solid to form char, or with hydrogen, for example, to form a useful product?
Gee, I don't have any idea what the lifetime would be, but I would think it would be a matter of seconds or microseconds, because the minute these free radicals are formed, they're very reactive entities, and I think they would be inclined to probably start reacting with the first thing they collide with, and with the liquid phase around, the first thing they probably collide with would be some of the liquid components. So to me it seems, perhaps very naively, that the presence of hydrogen donors, such again as tetra, and I mention this only as an example. I'm not an organic chemist, so when I remember one organic name, I'm very proud of it, so I will mention tetron as a typical example. The presence of these in any solvent, the minute the free radicals are formed by the pyrolysis process, would be a big item in contributing to the closing off of those radicals and the preventing of their going into char by further polymerization. So I would think it would be almost a matter of the next collision of these free radicals, and probably therefore something in the order of milliseconds or milliseconds or microseconds. Are there any other questions? Yes.
There's a point about that. If the free radicals recombine with each other, they'll disappear. But if it just abstracts hydrogen or something else from a saturated molecule, you'll be left with another free radical. If you're thinking
the saturated molecule can form the naphthalene and also be closed off. It can donate up to 4 hydrogens and then form naphthalene.
It forms naphthalene instead of another free radical. In other words, if you want to call naphthalene a free radical, all right, but it...
Not the first time the first hydrogen leaves it.
Oh, you mean when it gets... well, that's a good question. What happens when you pass hydrogens out one at a time from tetron? Do you... I'm not a good enough organic chemist to know if there's a stable compound that can exist with 3 hydrogens and 2 hydrogens and 1 hydrogen, or whether this is a sort of an unstable mess that loses all 4 hydrogens more or less simultaneously. I just don't know about this. But the blocking off of the radicals by hydrogen, I would think, would tend to form, well, it would tend to take 2 radicals out of existence and form whatever is formed when tetron loses hydrogen on the way to naphthalene. So it would diminish the radical concentration in any case, I guess, wouldn't it? Even if you form 1 radical from the tetron, if you call the 3 hydrogen thing a radical, for each hydrogen, each pair of hydrogens donated, it would decrease the net radical content. Are you still satisfied? You don't look very happy.
You look at me?
Yeah, you.
My guess is, first thing is that would be 1 radical, and when that gets attacked the second time, then there will be an even number of electrons. It probably is either stable or at least not a free radical.
So if you give 2 hydrogens up from the tetron, you probably form a stable compound and get rid of 2 radicals. I don't know. There's a detail I've done.
Yes. There's all sorts of opportunities for it.
This is right. And I guess I simply visualize that with a coal being a huge molecule of the type I represented this morning, or something different from what I represented, it's quite clear that there are a number of bonds that can break rather easily, and these CH2 bonds are picked on as some that might break rather easily, and thereby form effectively radicals for the time being. I mean, this must be taking place at an enormous rate in any pyrolysis process. Are there any other questions? Make them as complicated as you want, because I'm sure we have a field of experts here in the house that can answer them.
Do you consider it likely that most of the coal conversion processes, including those that use catalysts, actually go through a pyrolysis stage, and that the catalyst may just promote hydrogen donation to stabilize the free radical rather than the catalyst promoting the breaking of the coal itself?
Well, I think that's a very good question, because the thing that has occurred to a great many people is that if you try to use a catalyst in any system for handling coal in any way whatsoever, you have the product, you have the difficulty of contact between a solid catalyst and a solid coal material that you're going to work upon. Now, in some fashion, you have to bring the particular bonds that you want operated on in contact with the catalyst. If one has a liquid solvent such as in the synthol process that we're going to consider day after tomorrow. This can act as a medium for transferring sections of these molecules, which can then come in contact with the catalyst. Right in this connection, though, I can't refrain from mentioning something that has excited me very much, and that's the very lovely work that Terry Baker, I think his name is Terry Baker, from the Harwell Laboratories, has been showing around the country during this last year. I don't know whether any of you had a chance to see it or not, but he was working on the oxidation of graphite, and he showed pictures. He had an electron microscope rigged up with about a 25 angstrom resolution, tied in with a television, with a movie camera in such a way that he could see the surface quite clearly down to a refinement of something in the order of 25 angstroms. Now, this graphite surface, he covered with a few platinum atoms, not platinum atoms, platinum crystallites, the order of 80 to 100 angstroms in size, or palladium, either one, and then gradually heated the material up to around 500 degrees in some low pressure of oxygen, at which point these particles, which we would consider just as isolated particles on the surface, began to act like lawnmowers. In fact, the first gasp from the audience was, "My Lord, that'd be a good lawnmower," because they proceed to scrape over the surface, looping back on themselves without leaving any gap at all, and simply going back and forth, digging a trench into the graphite about half the size of the particle, and after a while they would cut off into another direction and go this way and so forth. But this showed that the particles, under these conditions, apparently being jet propelled by gases coming off one side of the crystal, were able to move around and contact the surface. And I have continually wondered whether anything of the sort might prevail in a thing like coal. That some of these particles that we put on as catalysts, when you get up particularly to the point of gasification or up in the range in which the coal is beginning to soften, some of the material might move around, even on the solid coal, according to this graphite work, might move around under the influence of jet propulsion. All it needs is an exothermic reaction. Any exothermic reaction apparently can propel these particles. Nobody's explained how it works, but one can assume that one side of these crystallites might be more active catalytically than another. And so that particular active side just is a continuous source of hot molecules which propel the particle in the other direction. Any of you who ever get a chance to see this would be fully rewarded by so doing, and I would like to see some of the work continued in this country, and it is pertinent to the question you ask of how the coal material gets in contact with the catalyst. And the answer is, as far as we know now, it either has to go through the gas phase or through the liquid phase. I don't yet know that the catalyst is running around in particles the way I'm describing platinum on graphite, but it's something to keep in mind. Any other questions? Some people here, I've talked to some, I forget who it was now, somebody I talked to had been to the Src plant. Do you care to make any comments on the, who was it?
Maybe you refer to me.
I think I was referring to you. Do you have any remarks that you would like to make on the plant? You see, they're very cold when you just look at them in a book and get the description out of a book, and I think a chance to see one of these plants operating would be very interesting to the group.
Yes, it's an interesting plant. One of the problems that they're having is operation of the filter, which separates the unreacted solids and matter from the liquid product. So they're using a fundo filter, which is made in Switzerland. It operates at 150 pounds pressure. It has a series of plates which are circular, mounted on a shaft which can be rotated. The shaft is rotated after the pickup cycle is completed in order to remove the cake on the surfaces of the filter. The cake is discharged inside the vessel which holds the whole assembly, and then the cake falls out the bottom. Other types of filters are being considered. The pilot plant, which is being built near Tacoma, Washington, will use a rotary pre-coat filter.
here at Oak Ridge, we're going to be looking at possible techniques for separating the solids from the liquids other than filtration. The pilot plant at Wilsonville, Alabama seems to work very well. There's some question about whether the product will be economically usable as a boiler fuel. It may not be economically competitive with stack gas scrubbing for plants which have the alternative of using high sulfur coal or solvent palm coal. But it probably will be competitive in the case of plants that have to operate on low sulfur fuel oil because they're located in urban areas. That's what I have to say.
Good, thanks. Yes.
How is this oxygen reacted with the coal in order to prevent the coal from caking? Is there special high-temperature treatment involved?
Why, the particular article which is described in this book called Fuel Gasification, the particular article describes the process in which, well, there are two articles. One in which they simply drop the coal particles through a stream of air at a given velocity and a given furnace temperature. The other one in which they fluidize the coal particles in oxygen, in a stream of oxygen for a certain length of time. But simply dropping them through a hot zone for a few seconds time of contact is enough to give the coating of the oxygen that's treated.
So there is a high temperature involved.
That's right. As a matter of fact, one of the articles is a decaking of coal in free fall by Forney, Gassior, and Field of the Pittsburgh Bureau of Mines. And the other one is from the Institute of Gas Technology by Kavlik and Lee. This group using the fluidized bed. The ones who use the straight fall procedure for treating the coal have a furnace at 600 or 700 degrees centigrade, though the coal temperature apparently doesn't get up above 350 or 400 degrees centigrade in the process.
I'm interested in, say, the fundamentals of what would happen in a surface reaction.
Well, I think that would be very interesting, and my first jab in that direction is to point out that if a cubic foot of oxygen is required per pound of coal, it's about the amount that one would need for a surface monolayer. Now, this is within a factor of 2 because the coal surface can be, if it's bituminous, anywhere from 150 to 300 square meters per gram. And I just make a guess in between. So, but if one did this experiment with known surface areas, one would be able to follow very well whether the amount of oxygen picked up was comparable to that. I think in terms of monolayers, because that's the first place that the oxygen is likely to go, assuming that the cracks and crevices are large enough to permit oxygen diffusion in at all. Otherwise, it might just go on the outside of the gross particle and perhaps all is found there. But I think it's an interesting correlation. Whether it's significant or not remains to be seen. Yes?
This oxygen pre-treating, do you have any information on what the effect of this pre-treatment would have on the yields of the pyrolysis reaction?
I don't on the pyrolysis reaction. Interestingly enough, I do have on this iodine hydrogenation at 200 degrees. The result there is that the first small treatment with oxygen steps up the yield of fluids from 34 to 39%, from a figure of 34% to a figure of 39%. Then additional oxidation for long periods of time drop it on down to 10% or so. So that after the oxygen's had a chance to work on the surface very extensively, the system is much less reactive so far as hydrogenation is concerned. But I don't know at all how it affects pyrolysis. I believe this same caking prevention is used in the the Pittsburgh outfit, the Toxic. What's the first name that goes with Toxic? Copper's Toxic Process. I think they deliberately pre-treat, or either that or the synthane process, maybe it's the Bureau of Mines synthane process. In one of the two, they pre-treat their coal prior to combustion. So the pre-treatment apparently doesn't interfere with combustion, but I don't know what effect it has on pyrolysis. I don't know of any work that's been done on it at all. Are there? Yes.
mentioned that the chars have very low surface areas of the order of a square meter per gram, but if then you oxidize them with water or air or what have you, you get very high surface areas in the charcoals.
Yes, I don't have that paper with me, but
Any explanation as to how this extremely selective oxidation can occur to drive up the surface area to these fantastic numbers?
well, only in the sense that this is a process that was used to make some of the best charcoal during the war. The Pittsburgh Coke and Chemical charcoal was made by taking a char from coal and heating it in controlled amounts of air. And all I could say would be that the oxygen probably proceeds down any pore structure that exists and burns its way as it goes and simply makes big holes out of small ones. In other words, that in case of wood charcoal, when you pre-treat with air, there are certain fibers in the wood along which the oxidation takes place preferentially, and so they drill holes in the char, in the wood char, very selectively, and presumably there must be irregularities enough in the coal to permit the same sort of thing to happen. In other words, it does burn down dislocations and the like, rather than just burning from the outside. Otherwise, there'd be no porosity developed. And the porosity goes up from the order of 6, 7, or 8 square meters per gram to figures I'm remembering in this particular work went up to 200 or 300 square meters per gram, but this is really just one step in getting charcoal, which goes on up to more like 1,000 square meters per gram, so that the char can be opened up to give charcoal very effectively. And
It's actually burning out just about every second layer or so.
yes,
It's impossible to get up to these enormous.
you see, if you just burn a single extra layer, in other words, if your capillaries are 5 angstroms to begin with and you make them 10 angstroms or 15 angstroms, this will open them up to give you this huge area. Instantly, I was talking about nitrogen areas when I said that they were down to 5 or 6 square angstroms. In other words, this didn't permit the expansion that's necessary to give the large surface areas of room temperature. I'm talking nitrogen areas when I talk of the char now. And the surface that's opened up, these are all nitrogen areas. Are there any other questions? We still have 5 minutes on that tape. Well, if not, I guess we'll stop.